So this is a showcase of the ECGR 3120 Inkjet printer project. I'm going to be showing how you run the code and then just showing the results for part 1, 2, 3, 4, A, B, C, D, E, and part 5. So to run the code, you download it from the GitHub, which is also in the report. And it also has all the results in here, and there's a separate report that is submitted in Canvas. So once you download the code and you have it open on a terminal, you just run pip-env shell and pip-env install. This one will install everything for you. Once that's done, you open this up in Visual Studio Code or something like that, and you can execute one by one each of the portions. So this basically imports all the necessary libraries. This sets all the constants that were given, and each of these parts will run. So for example, this one says like calculations for part 1. This will, literally do the calculation, and then this will give you the output. Question 2 plots the output, question 3 plots, and so on. So I'll show that the code runs. So this just is for part 1, where it's just doing a droplet, and the animation shown here. And it gives the time, which is 0.00015 seconds to draw. So here it draws the letter I. For all these videos, there's an option to either show it live or to save them to MP4s, which I've done over here in the video section. So these are like pre-rendered, because some of these animations can take a while to run. And for the video, I'm going to just showcase each of these instead of having the animations run for however long they take. So for question 2, that's something similar. You can see the droplet moving down to the bottom of the paper, and then the next one follows it soon after because of the changing voltages. So if I go to the video itself, this is like a sped up version of that. So as we can see, the voltage is varying each time. So one gets shot, once it reaches the paper, the next one gets shot, and each time the voltage gets lowered. It was determined that the voltage was about 2300 volts, and this lowers by 80 each. And it took 0.009 seconds to draw a 5.28 millimeter long eye. So for this question 3, it was kind of already done in question 2. I made it as large as possible, so it's going to be about 5.28. And I also sped this up, so as the second one leaves the capacitor, as the first droplet leaves the capacitor, the next one enters. So this code is pretty similar. The animation is slightly different, and there's also a plot of the voltage over time. So as you can see, as one leaves, the next one enters, and the voltage over time, so it starts at 2300, ends at negative 2300. So if I show the full animation here, as you can see, the results will end up being the same. It just takes basically half as long, because one's in motion while the next one gets fired, so it's a lot more efficient. Yeah, it took 0.0045 seconds, so literally half. Question 4 had, I think, 5 parts, so this is one where for part A we changed the distance between the capacitor and L2, so like end of the capacitor to the paper, by 3 times. So the voltage over time is plotted, and so is the graph. So as we can see, distance is twice as long, and looking at the voltage over time, looks pretty similar. the difference is that when it's each step size is less, and there's also more droplets that in the end get fired because the trajectories of these change. So like these droplets wind up going farther than they did before. If I show the animation, it ends up being, I think I calculated 128 droplets that fire to make this, because the size significantly increases, the max size of the letter I significantly increases. So as you can see, the voltage is varying. I'm gonna start, and this is at the middle of the paper, so this ends up being roughly if we go down to the results, it ended up being about 14 to 15 millimeters long, and it took 0.023 seconds to run. So for this portion, this is when L1 is increased, so the distance between the cannon and the start of the capacitor. In the end, this ends up just slowing down everything because the droplets haven't traveled a larger distance, and the trajectory where it lands is the same. So if I run the animation, that was pre-rendered. So like we can see that the distance is increased, and overall it just takes longer for these droplets to have to get over there. Like there's no real difference other than the amount of time it takes change. So the size is the same, but it took 0.00639 seconds instead of 0.0045. So this time the droplet diameter is tenfold increased. The voltage had to be significantly stepped up for this because the force on the droplet, because otherwise it wouldn't fire correctly. So as we can see, the droplets got significantly larger, and we can also see the print resolution, like the niceness of it decreased. So because it was 10 times larger, you could basically assume that you only need like 6 dots for this to draw the right size. So we also had to have a much larger voltage, so we could see like, I think it's like 100,000 volts instead of like the 2,000, because these are so much larger. And yeah. Now for this part, this is where we increase the velocity by 2 times out of the cannon. So now it's 40 meters per second, or 40,000 millimeters per second. So, oops. This had the wrong thing on. Let me just rerun this for a second. I had the wrong setting on it. So we can see that overall this plot's about twice as quick because it's moving twice as quick. However, one downside is that the voltage had to be stepped up much higher because the amount of time the droplet spends in the capacitor is significantly decreased since it's spending half as much time. So you need to step up the voltage so it can actually like have a meaningful effect on the trajectory. Yeah. That was that animation. Now for this one, this is where we increase the charge of the droplet by 5 times. Everything else stays the same. So with the charge now increased 5 times, we can see that the voltage steps look the same, but if you look at the scale, it's like negative, I don't know, 450, 480 I think it was, to positive 480. So because the drops have 5 times more charge, there'd be 5 times more force on them if we use the original size. Yeah, and for question 5, this is where we had to add a second pair of parallel plates to now affect it on the y-axis. So my first pair was on the z-axis, so now I put a second pair on the y-axis that is just as big, so symmetrically big as the other pair. So this allows me to use the same voltage steps and the same voltages. So for this portion, it's basically like drawing 3 separate eyes. So the first portion gets drawn like where the plate on the y-axis has its voltage completely maxed out, while the plates on the z-axis have its varying voltage. And the second line is, you know, the opposite, where it's all the way on the left, so the voltage of the y-axis plates are reversed. And for the third line, it is just a horizontal line, so the z-axis plates have 0 voltage applied to them, so that it doesn't affect where it's being drawn. And the y-axis plates have their voltage being varied. So if I show off this animation, it's going to show 3 graphs to better show what I'm talking about. So as we can see, there's now 2 pairs of parallel plates, and they're being drawn to that side over there. We can see that the voltage over time, this is what it will look like, where for the z-axis it goes down like that, so that's for the first portion. It goes back up and does the same thing for the second portion, and then stays the same. And for the y-axis, it stays constant at very high voltage, at a very high voltage, but in the opposite polarity, and then it steps down. So we can also see that this works perfectly fine. If we look at the trajectories from our angle, you can see how it's being affected like that. And for each of these, if you, when they're run, you can move around like this, so you can actually look at the droplet moving. Yeah, I think it's pretty cool. If I close these and I show the full animation, because this animation does take longer since you're basically firing 3 times the amount of drops. I think it was 180 droplets. So as I said before, it basically draws an eye all the way on the right side, like it's the max it can. And then it switches to the left side and does the exact same thing, making sure that they're the same height. And then the third portion is where it draws just a horizontal line like this. So the z-axis plates are off, while the y-axis plates are the voltage is varying for that. So as you can see, it's a perfect gauge, basically. And yeah, that took 0.027 seconds. So obviously it took longer, but you get a better letter. So again, this entire project is found in the GitHub with all the animations, the results, and all the graphs. All the graphs and a write-up is included in the report, which will be submitted to this after the voltage is recorded. Okay, thank you.